Now, in our next example, please consider the following system where we have a unity feedback and the following transfer function. So it is given as 21s plus 13k divided by s times s squared plus 10s plus k. And what we would like to do is to determine the range of k so that the closed-loop system is stable in the first part, and in the second part, for k is equal to 10, find the number of closed poles satisfying that their real parts is between -2 and 0. And we can start by writing the closed-loop transfer function right with this question. So I can start writing here g closed loop of s is equal to g of s divided by 1 plus g of s, h of s. H of s is equal to 1. So that will be equal to 21s plus 13k divided by s cubed plus 10, and that is equal to 21s plus 13k divided by s cubed plus 10 s squared plus k plus 21s plus 13k. Okay, so what we are interested in is to make the closed-loop system stable, and this is the denominator of our transfer function, closed-loop transfer function, and we would like these roots of this denominator to be on the left half plane, right? So I can construct the Routh array for this polynomial, for the denominator over here. So I can start from the s cubed term and the s squared term and s to the power 1 and s to the power 0. And can have the corresponding coefficients of the Routh array. I will start with the coefficient of s cubed, which is equal to 1. I will continue with the coefficient of s term, which is equal to k plus 21. And in the second row, I start with the coefficient of s squared, which is equal to 10. And I will continue with the constant term, which is equal to 13k. So this term over here is going to be equal to what's 10k plus, 210 minus 13k divided by 10. So that is equal to 21 minus 3k divided by 10. So if I go back there and try to write it down, so this is equal to 21 minus 3k divided by 10. Since this is equal to 0, if you make the computations over here, this 13k, because of that 0, will come here directly. Okay. And for the closed-loop system to be stable, I need to assure that the first row of the Routh array are all positive, right? So I need to have the condition, first of all, write it with another color. So the condition should be 13k should be greater than 0, which necessitates k is greater than 0, and 20 minus 3k over 10, 3k over 10 is greater than 0, which means that 3k over 10 is less than 21, and from there k should be less than 70. And from those two, It's difficult to do this parenthesis, but I will try once again. Anyhow, so from there I can say that k should be between 0 and 70 to assure that the closed-loop system is stable. So in part B, k is equal to 10, and it says that find the number of closed poles satisfying the condition that -2 less than real part of s less than 0. So first of all, when k is equal to 10, it's a value between 0 and 70, so the system is stable, right? So when k is equal to 10, we found that system is stable. So, which means that all poles are on the open left-half plane, right? So let me try to plot that if possible. So let that be the S-plane. And we already know that since the system is stable, all poles are somewhere over here. Okay. And the question is, if this is the -2, how many poles are there in this shaded area over here? Okay. So the system is third order, so there are 3 poles. Oops. So there are 3 poles in the left half plane, and we are wondering how many of them are in this region. So in order to do that, I have to apply some non-standard techniques in the sense that, so what do I have with the route array method is this. So if I have a polynomial, sorry about that, I can find how many poles are on the right half plane and how many poles are on the left half plane. How many poles have positive real parts, how many poles have negative real parts. So I can only compare with the 0 line over here. So I can only compare any polynomial with the real part of any polynomial with 0 over there. But the good thing is, so I cannot change that method, but I can apply it to any polynomial. And suppose I have a polynomial like this. So let this be a polynomial. Okay, so let this guy be d of s. Okay, so let's say d of s has roots at 0.1 and it has roots at like 3.1. All right. So the thing is that I cannot know if d of s has poles less than -2 or whatever, but what I can do is that I can shift around d of s and try to check if that shifted polynomial has roots with positive real parts or not. So in the sense that if you inspect, for example, d of s -2 here, so if that was d of s, maybe I should give more place there. So if this was d of s, so d of s -2 is going to be something like this, right? So d of s -2 is going to be 2.1 and 5.1, right? And notice that if, let me try to write over here. So if d of s has roots or poles greater than 0, then d of s -2 has poles greater than 2. Because here are the poles 0.1 and 3.1. Now they are greater than 2 because we shifted it by 2. And here I need another parenthesis. And in a similar way, for example, if d of s minus 2 has poles which are greater than 0, then d of s has poles greater than minus 2. So here I can write shifting. Okay, so then let me try to continue down here. Now one idea might be I still can apply the Routh theory to find the number of poles which have real parts greater than minus 2, is to define a new polynomial. I will call this polynomial as d bar of s. Okay, and I will say d bar of s is equal to d of s minus 2. D of s minus 2. And if I apply Routh-Hurwitz method on d bar of s and find how many poles d bar of s greater than 0, I will also find how many poles d of s have real parts greater than minus 2. So let me try to write down d bar of s. So then d bar of s is equal to, so I need to go back and write down, this was d of s, right? S cubed plus 10s squared plus k plus 21s plus 13k. And instead of s, I need to write s minus 2. So I will do it over here. Oops. I sometimes change the width of the pen by mistake. Then it's difficult to readjust it. Okay, so it is d of s minus 2, so it will be equal to s minus 2 cube plus 10 s minus 2 square plus 31 s minus 2 equal to 10. So if we replace k here, so that we have compact terms, I'll have s cubed minus 6s squared plus 12s minus 8. Then I will have plus 10s squared plus, minus 40s plus 40 plus 31s minus 62 plus 130. And that is equal to, so here is the s cube and the s squared terms are s squared terms here. So it is plus 4s squared and the s terms are here, there, and there. So it is minus 40 minus 9 plus 3, okay, so plus 3s, and the constant terms are 130, 40, 170, minus 8, minus 70 is 100, okay, so that's also 100. Okay, so now I do have d bar s, and I can apply the Routh ray technique for the d bar of s. Let me do that. So I will have, I can go down a little bit so that I can write more comfortably. I will start from the s cubed term, then the s squared term, s to the power 1, and s to the power 0. And write down the coefficient of s cubed 1, write down the coefficient of s term 3, write down the coefficient of s squared 4, write down the coefficient of s to the power 0, 100. And this is equal to 12 minus 100, it's minus 88 divided by 4 is equal to minus 22. And since this is equal to 0, this will, if you do the computations, that will appear as 100. Good, so what I do need now is to inspect the first row of the Routh tray. So I will do that. And if you inspect the first of the Routh tray, I need to check the number of sign chains. So from 1 to 4, no sign chains. From 4 to minus 22, there is one sign change. Sorry. This is plus one sign change. And from minus 22 to 100, there is another sign change. So I have a total of 2 sign chains, Then d bar of S has 2 roots with positive real parts. And as a result of that, d of has, I can write it down here, then d of S has 2 roots with real parts greater than minus 2. So apparently we were looking for how many poles of d of S was in this region between they have real parts between minus 2 and 0, and apparently only two of them have real parts between minus 2 and 0, and the remaining pole is somewhere over here, because for k is equal to 10 there are 3 poles on the left half plane, and we know 2 of them are here. Good.